We present less is more, reducing task and model complexity for 3D point cloud semantic segmentation. For 3D point cloud semantic segmentation, previous work often employs relatively large backbone networks to improve segmentation accuracy at the expense of computational costs. To address these issues, we propose a new pipeline that employs a smaller architecture, requiring fewer annotations to achieve superior accuracy compared to contemporary approaches. Our method has a 2.3 times model size reduction and about 600 times fewer multiply adds. Overall, our contributions can be summarized as follows. A novel method for LiDAR segmentation that uses significantly less parameters and offers superior accuracy. A novel SDSC module to reduce trainable network parameters. A novel ST-RFD strategy to extract a diverse subset for training by removing temporal redundancy. A novel soft pseudo-labeling method informed by LiDAR reflectivity to facilitate effective use of limited annotation. Our proposed architecture involves 3 stages: training, pseudo-labeling, and distillation with unreliable learning. In the training stage, we utilize reflectivity prior descriptors and adapt the mean teacher framework to generate high-quality pseudo-labels. In the pseudo-labeling stage, we fix the trained teacher model prediction in a CRB manner, expanding dataset with reflectivity during test time. In the distillation and unreliable learning, we train on the generated pseudo-labels, and utilize unreliable pseudo-labels in a memory bank for improved discrimination. The first contribution of our work is the SDSC module within 3D point cloud semantic segmentation. It is proposed based on the observation that depthwise separable convolution has shown results comparable with regular convolution, but with significantly fewer trainable parameters. We first take 3D voxels as input. We then go through the sparse depthwise convolution to perform the convolution with the trainable parameter reduction. Finally, we go through the sparse pointwise convolution to mix the information across different channels. With this module, our method has a smaller model size and fewer operations while keeping almost the same accuracy. The second contribution is the ST-RFD strategy. It extracts a maximally diverse data subset for training by removing temporal redundancy and hence future annotation requirements. It is conducted inside each temporal continuous LiDAR sequence. First, we evenly divide p-point cloud frames in each sequence into several subsets. We compute the similarity between temporally adjacent frames. The popular practice of semi-supervised semantic segmentation approaches is to uniformly sample certain % of the available annotated training frames, without considering any redundancy resulting from temporary periods of stationary capture or multipass repetition. While our ST-RFD strategy measures the spatio-temporal redundancy by the overlap within time continuous LiDAR frames, if the spatio overlap among some continuous frames is high due to the redundancy, multiple representative frames can be subsampled for training. It can thus significantly reduce both training data set size and redundant training computation. The third contribution is using unreliable pseudo-labels to make full use of all available labels. Unreliable pseudo-labels are frequently eliminated from semi-supervised learning tasks or have their weights decreased to minimize performance loss. However, such a simplistic discarding of unreliable pseudo-labels may lead to valuable information loss, as unreliable pseudo-labels can offer information that helps in discrimination. As shown in this figure, the unreliable pseudo-predictions show a similar level of confidence on car and truck classes, whilst being sure the voxel cannot be pole or road. To obtain minimal accuracy degradation, despite very few weak labels, we propose a test time augmentation, TTA, that does not depend on any label, but only relies on a feature of original LiDAR points themselves, namely reflectivity. Intuitively speaking, reflectivity is a distance-normalized intensity feature. To utilize the reflectivity features, we apply various sizes of bins in cylindrical coordinates to analyze the intrinsic point distribution at varying resolutions. We then normalize it and append to the point set for training. Here shows the qualitative results. This is the ground truth. Areas of improvement are highlighted in green, while the areas of not satisfactory are in red. Our model performs very well on small ratio sampling splits. For example, 5% and 10%. 40% results shows our method can even accurately segment many details, such as poles and intersections. Here we show another scene. Results on small ratio sampling splits might not perform well on small objects. For example, walls and street lamps. As the ratio of sampling splits increases, the segmentation accuracy of our method also increases. Here we show the qualitative video of 5% label frames. The yellow highlight areas show our method can achieve better segmentation results than other methods, especially in the category of vegetation, fence, sidewalk, etc. More visualization results can be found in our supplementary materials. For quantitative analysis, we present the performance of our approach, both with and without SDSC module in a side-by-side comparison with state-of-the-art approaches. Our approach offers superior or comparable performance across all sampling ratios. We also ablate each component of our approach step by step. We provide two models, one without SDSC and one with, corresponding to the bottom two rows. We compare our two models with recent state-of-the-art methods under 5% labeled semi-supervised training. Our model outperforms the voxel-based methods, with at least a 2.3 times reduction in model size, and up to 600 times fewer multiplied operations. We illustrate the effectiveness of our ST-RFD strategy by comparing our method with two widely used strategies in semi-supervised training, that is, random sampling and uniform sampling. Whilst uniform and random sampling have comparable results on both validation sets, simply applying our strategy improves the baseline results. To illustrate the improvements of using unreliable pseudo-labels, we evaluate selecting negative candidates with different reliability. The unreliable selecting of negative candidates outperforms other alternatives, showing the positive performance impact of unreliable pseudo-labels. We compare our performance with and without reflectivity in different sampling ratio. The results show that LiDAR intensity feature, in place of the distance normalized reflectivity feature, can offer inferior on-task performance. Our code and paper has been released on GitHub and the project homepage. Please feel free to contact us.